Bueno, buenas tardes a todas y todos. Vamos a dar inicio a un seminario más de la maestría. En esta ocasión, pues tenemos el gusto de tener aquí a unos invitados de la Universidad Politécnica de Silesia, el doctor Waldemar Mucha y la doctora Orsa. Y me voy a permitir pues, leer una breve reseña de ambos para que todos ustedes pues, puedan conocerlos un poco más. La charla va a empezar con el doctor Waldemar Mucha, quien es profesor del Instituto de Mecánica Computacional e Ingeniería de la Facultad de Ingeniería Mecánica en la Universidad Politécnica de Silesia en Polonia. Sus intereses de investigación incluyen el modelado, la simulación y el análisis de estructuras compuestas con redes neuronales, inteligencia artificial, así como la optimización a través de algoritmos inspirados en la biología. Mientras que la doctora Ana Corsa es profesora del mismo instituto de la Universidad Politécnica de Silesia en Polonia. Sus intereses de investigación incluyen el modelado de transferencia de calor en tejidos biológicos utilizando métodos numéricos no convencionales y métodos SIMAI. Entonces, es un placer para todos nosotros aquí en el CIMA tenerlos como invitados y como ponentes de este seminario. So, welcome, profesor Waldemar Mucha. We are glad to have you here in the Research Center for Applied Mathematics. So, you can start with the presentation.
Hey, thank you, Professor Felix, for the introduction. I'm very happy to be here. So, buenas tardes to everyone in Polish, dobry wieczór. So, as Professor Felix said, I came to you from Poland. Poland is a country in the very central Europe. On the north, we have the Baltic Sea over here. It is Germany, Czech Republic, Ukraine. Poland is a much smaller country than Mexico. We have less than 40 million people, our population, but it's worth to see our country. I can encourage all of you to come to Poland. We have very diverse landscape. We have the Baltic Sea in the north. It is cold sea, but very rich in iodine, so very healthy to be there. We have the Amazonian Lake District in the center of Poland, so big lakes, lots of people go to sail there. And we have mountains in the south. Hiking is very popular sport in Poland. Our highest peak is about 2.5 kilometers over the sea level. Poland is not as warm as Mexico, so we have negative temperatures in the winter. Summers are not so hot. And together with Anna, we work at the Silesian University of Technology that is located in the south of Poland, in the most industrial region of Poland. It has campuses in 3 big cities, but the main campus is in Gliwice, where we work. Here are some statistics. We have about 20,000 students, less than 2,000 academic teachers, 15 faculties, about 600 PhD students. There are also some PhD programs, if some of you would be interested. PhD studies at our university are free, and you also get a scholarship. So if someone is interested, just send me an email. I can send some more details. We have 15 faculties. It is a technical university, so we only have technical faculties like electrical engineering, chemistry, civil engineering, automatic control faculty. We are from the Faculty of Mechanical Engineering. My professional experience, as Professor Felix said before, I work at the Department of Computational Mechanics and Engineering. So I deal with finite element modeling, computer-aided engineering software. Also, sometimes I deal with some experimental mechanics, like materials testing machines or strain gauges. And my greatest area of expertise lately is applications of artificial intelligence methods to mechanics, mainly optimization methods, and today I will be talking about optimization, and also artificial neural networks. So if after this presentation someone who is interested in some cooperation regarding these topics, so please contact me. So today I will be talking about optimization using evolutionary algorithms. Evolutionary algorithm is a non-conventional optimization method. The title is in structural mechanics because I deal in my work with structural mechanics, but this algorithm can be applied to every other applications. Before I talk about optimization, I know this is basic stuff, but let's talk about direct and inverse problems. So what is the difference between direct problem and inverse problem? Direct problem is when a knight is hunting dragons and a knight sees a dragon, then he knows what footprints would the dragon leave. Okay, this is a direct problem. But the inverse problem is when a knight sees the footprints and he needs to identify how the dragon looks like. So in order to solve the inverse problem, the knight needs to know solutions of many direct problems. Okay, and but this is just an imaginary example. What about some mechanical example? For example, we have a beam that is supported at one end and it's loaded at the other end. So a direct problem would be what is the deflection of such a beam? We can simulate it or solve it analytically, and we get the deflection. We get some maximal value. It's easy to solve. But an inverse problem would be that we know the result. We know that the beam deflects in such way, and how it is loaded and how it is supported to give such a result. This is an inverse problem. And to solve it, we need to know solutions of many direct problems to adjust the right model parameters. So this is an inverse problem. So you see here we have many different direct problem solutions, and then we can find the solution to the inverse problem. So we have maybe we have two classes of inverse problems. The example that I have just given was identification problem. That means that we know the results, but we don't know the model parameters that give such results, and we need to find the model parameters. This is identification problem. Also, there is optimization problem. Optimization problem is that we need to find the best possible result, and we find the model parameters to find the best possible result. So, for example, for this beam, we could look for a cross-section dimension, like the height, the width of the cross-section, the thicknesses. For example, for the beam to be as light as possible and withstand the force. So this would be an optimization problem. How to formulate such a problem mathematically? You are all mathematicians, so I think that this is nothing new for you. The most common approach of solving optimization problem is to formulate as a minimization. So we need to minimize a function. We need to find the global minimum of a function. And the function is of x. X is the vector of design variables. So these are the model parameters that we seek. For properties of the model, for example, in mechanics, geometry dimensions, some material properties, boundary conditions, etc. And the function f is called objective function. Okay. We can also maximize using optimization methods. We just have to flip the function with just most of the algorithms is for minimization. So if we want to maximize some criteria, we just need to flip the function and the algorithms will work. Sometimes we have constraints to our optimization. So for example, for the beam, the objective function would be the lowest mass of the beam, but the constraint would be that it should withstand the load. So this is the constraint. Optimization methods. Here are some of optimization methods listed. I believe that you know gradient methods. Gradient methods where we have a function, we need to calculate the derivatives of the function, and then we iterationally go to the in the direction of the highest decrease. But gradient methods don't work really well for certain problems. For example, if we don't have the function written mathematically, it is just the function is just a numerical simulation. So how to calculate derivatives of such a function? Or if the function is multimodal, that means it has a lot of local minima. So gradient methods tend to start with the nearest local minimum if they won't go to the global minimum. And so we have some unconventional optimization methods, bio-inspired. That means that the creators of these methods took inspiration in some mechanism of nature. And if it works in nature, it should also work in algorithms. So, for example, evolutionary algorithms, or particle swarm algorithms, or immune system optimization. Today, I'm going to be talking about evolutionary algorithms. So this is an optimization algorithm that is inspired by the Darwin's evolution of species. So how does the natural evolution work? So it happens by natural selection. Every individual varying their genes. So every one of us has different genes. And the individuals best suited to the environment are more likely to survive. They are more likely to find food, avoid predators, resist some diseases, and they are more likely to reproduce. And their genes will be passed to the next generation. And individuals that are poorly adapted are more likely to die, not to reproduce. They have smaller chances to survive, to pass their genes. So it happens in the animal world, in the human world. It was like this some time ago. So how does the algorithm work? Based on the same principles. So potential solutions are individuals. We work on a population of potential solutions to our problem. We have a population of potential solutions called individuals, and our function determines the environment. So we calculate the objective function for each individual, and the lower value means the better the individual, the potential solution is suited for the environment. And yeah, the algorithm works on a population, so a set of potential solutions, and the algorithm is iterative. So the population evolves in subsequent generations to better fit the environment. So in every subsequent generation, the potential solutions to our problem are better than in the previous. Here is the flowchart of the evolutionary algorithm. There are many versions of such algorithm, so this is just a general flowchart. So how does this work? Start the algorithm, we have initialization. So we have a population of, let's say, 20 individuals. We set a constant number. We have 20 individuals, and these are our potential solutions, so we generate them randomly. We create, for example, 20 models with random parameters. So for the beam, it would be 20 beams with different dimensions of the cross section, for the former example. Then we evaluate. So we need to calculate the objective function for each one. So that means that if you have 20 of them, we need to run 20 simulations. And every individual has the value. Here is a stopping condition, but let's skip that for now. Then we have selection. Selection means that some of the individuals will survive and some of them will die. But how does it work? Individuals with better fitness function value have bigger chances to survive. But it's not automatic that they will survive. They have just better chances. So here is like a lottery, but not a fair lottery, where some of them have better chances and some of them have poor chances. And after the selection, some of them survive, some of them are eliminated. So we need to recreate the whole population. We need to recreate the missing individuals, and it is done by crossover. That means that we randomly choose two potential solutions, and we mix their parameters to create a new individual, a new potential solution. So, for example, we take diamond from one individual, we take parameter A value, from the other we take parameter B value, and from that we create a new potential solution to our problem. But this wouldn't suffice, because if some features are not created here in this random process, we wouldn't get maybe the optimal solution. So also mutation is necessary. Mutation means random changes. Also in nature, mutation is like random changes to genes. So we have here probability usually allow between like 2 and 8% of applying a random change to a parameter of some of these potential solutions. And then we evaluate once more, and it goes on and on until the stopping condition is met. What is the stopping condition? For example, it could be that we reach good enough solution. So we say we need to find a structure that is lighter than 20 kilograms. So it could be our stopping condition. But also very popular stopping condition is if the generation does not improve. So the fitness value in evaluation doesn't improve in, let's say, 3 or 5 subsequent generations, then we stop, because we reach the optimum. Okay, it's easy if we have one criterion of optimization. For example, we seek the lowest mass. But what if we have more than one criterion and they are contradicting? For example, this is just an illustrative example. We are looking for a computational tool that has the highest performance and the lowest cost. So we cannot find one optimal solution to that, because we can find many potential solutions. And every of them will either be better or in one criterion or be better at other criterion. For example, here we are looking for two dig holes in the ground. Either we have lowest weight or highest productivity. So we can find many solutions to that problem. And this is called Pareto fruit. That means if we have, for example, function 1 and function 2, and we need to minimize both of these functions, then we get a Pareto fruit of the potential solutions, and we eliminate the yellow ones, because the yellow ones, if there exists at least one solution that is better in both criteria, then this will eliminate. Okay? So we always get a shape like this for two criteria. So the yellow ones are called dominated solutions. We eliminate them. And multi-objective optimization can be also solved using the evolutionary algorithms. There are versions of the evolutionary algorithms. It is an example, a mechanical example, of shape optimization of a thermal actuator, a microthermal actuator in MEMS system, micro-electromechanical systems. So this, you can see the scales, it is in micrometers. How do such actuators work? So here we have paths where we apply voltage, and then the current flows through the actuator. One arm is thin and one arm is thick. So the current density is different in both arms. So due to the Joule heating, one will heat to a higher temperature and the other will heat to a lower temperature. And because of the thermal expansion, it will bend. So when we apply voltage, it bends. And such actuators are applied in printheads, in inkjet printers, or in some medical devices like endoscopes, catheters, surgical instruments, also with some microwaves. So there are some specific applications. Here is simulation of an example, finite element simulation of an example actuator. And we wanted to optimize these actuators to have an optimal shape for certain criteria. So how is it applied in the software? Usually, in such cases, we use some CAE software like ANSYS or some MSC software or Abacus to solve a single model, to solve a direct problem. And then we need to connect it to our evolutionary algorithm. So we write the procedure, for example, in MATLAB or in Python, where the evolutionary algorithm is running. And to evaluate the fitness function each time, we call the finite element model by exchanging some data in the next files. And here are some material properties, some boundary conditions, but it is not very important. Just what we are trying to optimize. We are trying to find an actuator that can operate at minimum voltage, right? And we are trying to find an actuator that will heat to a minimal temperature, and we are trying to find an actuator that is it has maximum deflection, so it deflects maximally with lowest voltage and lowest temperatures. So these criteria are contradicting. And by using evolutionary algorithm, we found many potential solutions to the problem. Here are the design variables, are all the z's here. So all the z's, all the dimensions, the thicknesses, the lengths, everything. And we found many solutions that, and here are 2 of 3 criteria on this chart. So now we need to choose. If we want a solution with more deflection and highest temperature, or with less deflection and lower temperature, now it's up to us. Here is the Pareto front in the 3D space when we put together all 3 criteria. So such optimization could be performed using gradient algorithm. Also, I told you that we have 2 kinds of problems, inverse problems, optimization and identification. So identification can be also formulated as optimization problem, as a specific type of optimization. And the objective function that we minimize is as follows. We have the results of our potential solution, and we have our desired results, our known results, and we seek the model parameters that have exactly these results. So now we have the difference squared, and we minimize such function. And another example of this time identification problem formulated as optimization. So here we have an example structure. Here it is supported, here it's loaded, and it has a crack. And we don't know the location and the shape of the crack. But what we know are displacements at these points, at these red points. So let's say that here are some displacement sensors. And it was also identified using evolutionary algorithm. It is first generation when all the potential solutions are put together. So every crack is one potential solution. And then we run the evolutionary algorithm, and you see how it evolves in subsequent generations. And in the last generation, the best individual was the best individual has a very similar shape to the original crack. So identification can be also solved as optimization. That is all. So thank you for your attention.
Thank you, Waldemar. So, yes.
Thank you. If you have any questions, I am happy to answer.
Yes, please.
Yes.
Hi. So, first I want to say thank you for your exposition. I think explaining to us what is the evolutionary algorithms and the Pareto fronts is essential if we want to work something about optimization. And sometimes we don't have the experience about which applications can be part of or can produce by evolutionary algorithms. So I think your exposition is very interesting, and thank you very much.
Thank you. To answer this question, evolutionary algorithm works well if we have a multimodal problem. That means a problem with many local minima, and we need to find the global minimum. Also, when the objective function is not continuous, because non-continuous functions, it's hard to calculate the derivatives. And here in evolutionary algorithm, we don't need the derivatives. Also, when we don't have the function in the mathematical form, it's just the function is evaluated by a computer simulation. So also for such applications, evolutionary algorithm also work quite well.
you, Waldemar. We have time for another question.
Thank you for a nice presentation. I have two questions. The first one is related to the multi-objective problem. After you optimize the model and you have the Pareto problem or the approximation of the Pareto problem, how do you choose the solution or the approximated solution of the Pareto problem? And that's the first. And the second one is related to the second application, and it would be possible to implement or solve the identification problem instead as an optimization of using machine learning models.
Thank you. These are very good questions. So to answer your first question, how to choose one result from many? So this is just application based. So this is subjected to your specific case. The user needs to choose. If he wants a model where the first criterion is better or where the second criterion is better. So usually you choose from around here, but it's case specific based. What the evolutionary algorithm does is that it allows to eliminate all the dominated solutions. And we only have a set of non-dominated solutions. So this is the only thing that the evolutionary algorithm produces. And as for your second question about machine learning, it is also used both in identification and optimization programs. Here the bottleneck is the evaluation. So this takes a lot of computational time because we need to solve the objective function for each individual. And we have many individuals, many generations, so we could have hundreds or thousands of evaluations of the fitness function. And here we can use machine learning. So first, we can create a meta model, for example, a neural network that will approximate our solution. And so we can feed the network with some example input and output data, and it will, and we could have a very fast mathematical model, like machine learning model neural network, or some Gaussian process, or some state vector machine, or something else that will compute it here very fast. And then we can obtain solution from the evolutionary algorithm very quickly, but it will be only an approximated solution. But then we can use the gradient as a starting point from the approximated solution to find the exact solution.
Thank you.
Thank you, Professor Waldemar.